All right, we're going to take a look at lesson 3.2, which is about logarithms. Logarithms we're going to discover is the inverse of exponentials. But before we do that, let's remind ourselves of some exponentials. It says here, the number of downloads of a new song grows at a continuous exponential rate during the first days after the song's release, shown in the table. What is the song's growth rate during these 10 days? Okay, continuous is a very important word. What does that mean if it's continuous?
It keeps happening.
It keeps happening. There is a, I would say letter, but technically it's a number in math that represents something continually happening. Do you remember what letter that was?
The E.
The E. The E. This formula, whatever we come up with, giving away what we're about to do, has to have an E in it. All right, you have a table and it says, what's the song's growth rate? Meaning, what's its interest, or the R? How do you think we could just solve for that? What do we learn in lesson 3.1 that would help us come up with the rate? How about a model? Let's go use the model to figure out an equation. So let's go to our calculator, and we're going to use calculator number, which one? 7, the one with the table. That's right. The one with the table over there. And so let me just clear these other ones off. So, okay. So here's my table. They only give me 2 values. Don't worry about this saying t and this n of t. I'm just going to use x1 and y1. So they only give me 2 values, so I'll delete that second row. But we have 0 is the first time. The y is 300. And then I have 10 and 12, 1, 5, 0. I do not use a comma. It won't work with commas. So don't type in the comma. Ignore that comma. All right. Are we doing a quadratic regression or quadratic model? No. So I'm going to close this little triangle. Which triangle should I open up? Yep, I'm waiting for more students. Kalina's right. Anybody else can figure out which one to open up? It says continuous exponential. We're going to go to continuous exponential. Number 12 here. If you're looking on the left, line 12 is it. So I'm going to open that up, and you can click it just to see the model. But the equation, all that you need is right down here. It tells you clearly that the A, what does A represent in this formula? If it's at the very front. That's the starting amount. That's right. So it says the equation comes from, I know that it has a squiggly, but that is meaning, that's just a Desmos symbol to mean come up with a model here. The equation is 300 e to the power of, r is up there as a power. I'm just going to say 0.37. I'm going to round it to 0.37 x. I would say x, but it actually is a t, and I should change the y. No, it's not y, it's n of t. N of t represents y on this problem. So let's do that. N of t. There's our equation. And so what's the growth rate? Or what is the rate of growth? If it said 0.37, what is that as a percentage? 37%. You're correct. It's 37%. That would be the answer to number 1. That's a pretty good growth right there. Obviously, you look at it, you went from 300 downloads to 12,000 in 10 days. Yeah, it's growing pretty fast. I wish my money would do that. $300 turn into 12,000 in 10 days. That'd be nice. All right, number 2 here. The Martinez are saving for their son's college education. If they deposit $31,500 into an account, earning 7.6% per year compounded monthly, approximately how many years will it take for the value of the account to reach $80,000? We have a calculator to help us out on this. Which one should we use? Number 9. By the way, you could also, from Clever, if you go to my page from Clever, and you can see that I have in here a formula chart as well. If you want to do that nitty-gritty algebra, if you go to formula chart right there, you can click that if you want to do the algebra and plug in the values. But here's our 2 formulas down here. Which one are we doing? Is this being compounded all the time or a certain number of times per year? Per year. How many times per year? 12. 12, sweet. So now we know the formula we're going to use is this top formula. So instead of getting it from the formula chart, I'll just take it from right here. The formula is A equals P times 1 plus R divided by N raised to the power of NT. Again, that's on the formula chart, but it's also on my calculator. So I just got it from right there. Let's fill in. Did they give us a final amount on this problem?
Yes.
Yeah, what's the final amount? 80,000. That's my A, my final amount. So 80,000, and I'm not going to write the comma here because I'm not going to type it in the Desmos, so it'll mess it up. Okay, did they give us a starting amount? Yes, they did. 31,500. Parentheses 1 plus the rate is 7.6%. What is that mathematically equivalent to? So 7.6%. What you could do is divide that by 100%. Percents would cancel. So you could just type it in like that, or you can move the decimal over 2 places. I'll do that here. It'd be 0.76. So the decimal moves 2 to the left, 2 to the left. So over 7, and then you'd add a 0. So that's my rate, 0.076. This will be divided by how many times per month are we doing this? I'm sorry. How many times per year? That's our N right there. N will be 12 because it's monthly. And now finally, you raise it to the power of 12. And then how many years does this happen? We don't know. That's our unknown. So that's what's going to be in our calculator, the X. I'll just leave it as a T. So we come over here. The final amount we want is 80,000. The initial amount is 31,500. Notice on Desmos, you don't put in commas, but they will naturally give a little space where the comma would be. They'll do that for you. The rate we said is 0.076, which you could have done 7.6 divided by 100 right there as well. I'll just write it that way. You could do 7.6 divided by 100 if you don't want to make a mistake. Just let the calculator do the math. We don't know time, so what should we do for time? X. This one did have an N, so hit the little triangle to open that up and go to 12. Now I'm going to pause here this video. I'm going to let you, as I walk the room, I'm going to let you tell me how much money or how long it takes to solve. You will have to, no, wait, they won't get the answer here. You're going to have to graph it, but you're going to need to use, which formula are we using? The one with an E or the one without an E? Okay, so you'll need to click that. You'll need to scroll out until you see how long it takes for these to intersect each other. The answer is going to be that intersection, but I will let you discover that on your own. All right, make sure you round this to the nearest hundredth. And again, if you're not seeing the graph, it's because you have not clicked that little circle right there. So make sure you click that circle on the formula. The intersection will be your solution. I'm not going to click it because I'm not going to give it away, but it should be up at 80,000. So zoom out to 80,000. That's the amount you're looking for. Click that circle and then click the intersection for your solution. All right, let's take a look at lesson 3.2. So today is all about logarithms. And so this little sheet here, I actually gave you this on lesson 3.1. So I gave you this last lesson on 3.1. The way I wrote it is like this. I didn't just use symbols. I wrote it out. I said, we have a base raised to a power, and that's going to equal some, who remembers? Number. Very good. A base raised to some power equals a number. This is how I wrote it last class. And this is exponential. And I said exponentials happen to have an inverse. Their inverse is a logarithm. And if you really wanted to solve exponentials by hand using algebra, you need to use logarithms. Since you didn't know logarithms, I didn't do much of that yesterday. So the way you would do it is you first add in this word log, but then what would happen is you would have your base, and since it's an inverse, what's the definition of an inverse again? Switch x and y. What we learned last class is an exponential function is anything where the power is an x. Let me do it up here. As a power is your x or your variable. The number is by itself, so that's the y. What happens is these two switch spots. So instead of base raised to a power, it's going to look like the log with a base is raised to a number. and that'll equal the power. So yes, I told you we did write this on the notes last class. You're right. So what happens though is it switches the x and y. That's what they're doing here with the x and y. Notice what they've done is they're just switching it, and this is the way we just saw it, had saw it, however the grammar is, last class, where you switch your x and y, and it looks like that. Now they just use the letters b, x, and y. Base x equals y, base y equals x, base to the power of y equals x. That's how they do it here, starting from the logarithm. I started with exponential because that's what you see more frequently. Okay, so that's what you see more frequently. So anyways, I showed you that last class. So now let's get started. Oh, one more thing. This part right here. What's this walking through? Or that, not right, that right here. Remember on our domain rules? The domain rules, I say assume all reals. You might want to go ahead and write this down. Assume all reals unless, and I've given you some rules. What was the first thing we talked about that would break up the domain?
Can't divide by 0.
Can't divide by 0. And so the way I symbolically show that is 1 divided by x cannot equal 0. Cannot divide by 0. You can write that out if you want. The second thing had to do with the square root. What's the deal with the square root? Can't be negative. That means it can be positive and it can be equal to 0, but it cannot be negative. Here's your third rule. We've been waiting for it. It comes today. A logarithm, the value that goes inside the logarithm, it doesn't matter the base. So I'm just going to leave the base blank. The value of the logarithm on the inside must be greater than 0. Said another way, the number has to be greater than 0. That means it cannot be negative, nor can it be 0. It must be positive. Okay, so you cannot divide by 0. You cannot have a negative square root. You cannot have a non-positive logarithm. I mean, it must be positive. There's your domain, your third rule. Now let's get going. So that should clarify your domain basically for the rest of your life. Now you know the 3 rules. All right, so first it says evaluate some logarithms. And I totally get we could use the calculator and just type this in. For those of you who have done this before, you can just type this in and it'll tell you the answer. We're not going to do it that way. I want to make sure you understand how it works. So what I'm going to do just to help us out is put an equals x here. Put equals x. If you wanted to evaluate this logarithm, what I would recommend is to switch it to exponential. So what's my base? 2. What's the power? Nope, that's the number. Remember that it goes log base number equals power. So what's my power? X, and that equals a number, 16. What I'm going to do is take my 16 and use what I call upside down division, where I ask myself, how many times can the base divide into 16? The base is 2. How many times can 2 divide into 16? 8. And I'm going to keep going and say, okay, now that I know that that's an 8, how many times can my base of 2 divide into 8? 4 times. How many times can my base of 2 divide into 4? 2. And you stop once you get all your base all the way across. This is 16 is equal to 2 to the 4th power. 16 equals 2 to the 4th power. So now if 2 to the power of x equals 2 to the 4th, we can clearly solve for x. X is equal to 4. I'm just going to get a blank calculator here and prove it to you. Like I said, to this whole lesson, basically you could just type in the calculator. Log, what I'm going to do is hold down the shift and press the minus button, shift minus, and it'll make me go low and I can type in that base. So I did shift, I held down shift and I pressed minus, and it takes you down low. Log with a little 2, then I press to the right to go big again. 16 equals 4. You can see the calculator agrees with us. I am no fool. I totally understand you can type in the calculator, but I want to show you how logarithms work as well. All right, part B here. Evaluate 5, or log base 5 of 125. Okay, so I'm going to convert this. So I'm going to say equals x. What is my base? 5. What's my power? X equals 1 over 125. Now, there's a few things you can do with this, but basically, here's what I'm going to tell you now. A negative power will make the base become its reciprocal. So a little trick here. There's a few things you could do here, but the one I'm going to do is I'm going to say 1/5 to the power of negative x equals 1 over 125. So what property did I just do there? This is an old algebra 2 property with powers or exponents that says if you make your exponent negative, you take the reciprocal of the base. So instead of this being 5 over 1, I made this 1/5 to the power of negative x. Okay, so now I want to know how many times can 1/5 go into 1 over 125. Now I know I have it written that way. What I'm actually going to do is 1 can go into 1 a million times. It can go in 1 time. But the 5 going into 125 is different. That's what I'm actually going to do here. I'm going to say how many times can 5 go into 125? I'm going to call the base for a moment 5. How many times can 5 go into 125? 25 times. So you ask yourself again, how many times can 5 go into 25? 5 times. Now that I'm at my base all the way across, you can confidently state that 125 is equal to 5. And how many 5s are there? 3. 5 cubed. So here's what that actually means for this problem is you can say 1/5 to the power of negative x is equal to 1/5 to the power of 3. Since it was cubed, you could write it that way. Or we could just come back to the top and say 5 to the power of x is equal to, now that I have this right here, 5 to the negative 3. Either way, it's going to be the same. Now, I don't know, I don't want to confuse you, but my answer, if negative x equals 3, what does positive x equal? X will equal negative 3. That's going to be my answer here. So what a negative and a power does is it just takes the reciprocal. So 5 cubed is 125. So 5 to the negative 3 would be 1 over 125. Now let's check that in the calculator, just because I got kind of confusing there. And did shift minus, log, shift minus goes low. Just like shift 6 goes high, shift minus goes low. And then I press to the right, 1 divided by 125. Whoa, that didn't work. Let me do a parenthesis around that 1. 1 divided by 125. There we go. Answer is negative 3. So we did do it correctly. All right. Let's do this one a little bit quicker this time. Does anybody know the answer off the top of their head without using calculator? You're close. It's not going to be 3. So 3 to the power of x. Now, a lot of you knew that 3 to the power of 3 is 27. So if you need it to be 1 over 27, you just make it negative. So our answer will be negative 3. Let's check it though. In case you did not know that, 3 divides into 27. I'm going to ignore the 1 for a moment. 3 divides into 27 how many times? 9. And again, you stick with the base of 3. 3 goes into 9 how many times? 3 times. You stop when you're got the base all the way across. So 27 equals 3 to the, there's 3 of these, third power. Now, if 27 is 3 to the third, that means 3 to the power of x is equivalent to, if that's 3 to the third, this would be 1 over 3 cubed this way, but these bases aren't the same. That's the same thing as 3 to the x equaling 3 to the negative third. And thus the answer is x equals negative 3. Now I'm writing a whole lot of steps out, showing you reminding you really, just because it's been 2 years and it's been 2 COVID school years. So a lot of us forgot the exponential rules. So that's why I'm trying to write it all out, but I might just be confusing you more than anything. I'm sorry about that. But you can see we did do it correctly. Yes, sir. Yes. 1/3 to the power of 3 is equivalent to 3 to the negative 3. And the reason being, 1 times 1 times 1 is still 1. So if it was 2/3 to the power 3, and you want to make it a negative power, you would need to make it 3/2 to the power of -3. Does that make sense?
Yeah.
So you take the reciprocal, but having 1, dividing by 1 doesn't do anything. Even if it's raised to a power, it's still dividing by 1. So that's why I just ignored that. Yeah, go for it. All right. Oh, I thought that was going to be done. I'm sorry. I got one more here. Let's do this one. 17 to the power of x, the base is 17, raised to the power of x equals 17. Any takers on what the answer is going to be this time? 1. X equals 1. Log shift minus little 17, go to the right, 17 does equal 1. All right, now this takes us to our first DOL. You can go for this one. All right, let's take a look. Some basic properties of logarithms. So logarithms, just to add a little wrinkle here, logarithms have some crazy properties that to a lot of people don't seem to make sense on the surface because they don't follow any other type of math. Meaning, if you're dealing with quadratics, you're dealing with cubic functions, you're dealing with trigonometry, they don't follow these same rules. It's just logarithms, what they are able to do. So think about it. They are inverses of exponentials. And remember the illustration I kept telling you last class that each and every one of you could become a millionaire if you wanted to? You remember that? Because exponentials get so large so fast. Logarithms are tricky because what they do is they take, because they're opposite, or not opposite, sorry, they're inverses. They don't take something small and make it big over time. They take something big and make it small. So they have some crazy properties attached because they're just different types of functions. So first off, a base raised to a power of 0 equals 1 always. So let me translate this using exponentials. A base raised to a power of 0. Any base raised to the power of 0 always equals 1. Okay, so that's here in log form, that's just walking through that. Anything raised to the power of 0. So I don't care what it is. What is 10 to the power of 0? 1. Good. What is 5 to the power of 0? What is x to the power of 0? 1. What is 1 to the power of 0? 1. Okay, anything raised to the power of 0 is 1. Secondly, any base raised to the power of 1, any base raised to the power raised equals its own base. I couldn't spit that out. Let me try that again. A base raised to a power of 1 equals just the base itself. That's what the second logarithm is walking through. Over here, the next one's saying a base raised to the power of x is going to equal the base raised to the power of x. I know that one's brilliant. The base raised to the power of x will be equal to the base raised to the power of x. Finally, I know, brilliant, brilliant stuff right there. This one is in exponential form. It's saying the base raised to the logarithm with the base raised to the number of x equals x. Again, like I said, they just kind of get confusing. But this is, if you wanted to transform this, you would say, okay, if you were going to that's an exponential. That's what's different here. This right here is not a logarithm. This one is exponential. And so if you really wanted to solve it, you would solve it to a logarithm. And so I'm going to add the word log that's not there. I know it has this log, but I'm adding that word log. And I'd ask you, what's the base in this little problem I circled? What's the base? What's the thing that has the power? The b. Remember, these two for the inverse would switch places. And so the number would go next. So this says log base b of x. And you would say that equals, what was the power? Log b of x. Do you see how they're now the exact same thing? So it's kind of, it looks complex, but that's really what it is. Okay, with that, let's look at some numbers because that typically goes better than properties. On this one, I'm going to continue on the same steps that I've been solving with. If I wanted to solve this without a calculator, what would I say? You would equal this to x. And so you would say, if you convert this to exponential, 8 to the power of x equals 512. So I'm going to use my upside down division to simplify 512. How many times does the base of 8 go into 512? 8 goes into 5, how many times? 0. 8 goes into 51, how many times?
7. Oh, 6.
6, very good. 6 with the remainder of 3. 8 goes into 32, how many times? 4. So it's 64, and then you continue on. How many times is the base 8? So as we were saying, 8 goes into 64, how many times? 8. And I realized when I went to cut that recording, I didn't finish my 8 here. There it is. And so we say 512 is the same thing as 8 cubed. And I'm going to erase this little 3 because later in the notes you're probably confused. What's that 3 there for? Okay, so the answer here is 8 to the power of x equals 8 to the power of 3. Again, I'm writing a whole lot of extra steps that I don't expect you to necessarily write, because you probably just know, oh, my answer is 3 from there. But that is correct. Log shift 6, base is 8 of 512. Answer is 3. That is correct. Whoops. There we go. All right, part B. Evaluate what in the world just happened. This looks so different. We could type it in, but we don't have to. What's different about this problem?
Logs and exponents.
They gave it to us in exponential. This is exponential. Go ahead and put that note there so you don't. This is exponential, because in the coming days, I'm not going to tell you, hey, today's all logarithms and we're going to convert. You're going to have them intermixed. This is exponential, which means if I wanted to solve an exponential right now, I have a base. Let me go ahead and label. What's the base? I'll call it just B for base. This right up here. That's the base always is raised to some power. I'll go ahead and write out power. I'll go ahead and write out base. I can do that. And that's going to equal some number, which is strange that I have an X representing the number, but that's what it is. So to solve this, you would add the word log, because you're changing it to a log. The base still goes first, which is 22. It's an inverse, so these two switch positions. So number is X equals log base 22 and number 15. So can you establish what the answer is? 15.2. Technically, we can see it. You haven't learned yet. I think it's actually next class. They tell you that is called a one-to-one. It's a property of logarithms that if you have the same, if one log with one base equal another log with the same base, then the number of values are equivalent to each other. That's technically a property that you haven't seen yet. But now let's just check it. I'm going to go type this in. 22 shift 6 goes up high. Log shift minus goes low. Base 22 15.2. Calculator says 15.2. All right, your turn. Go ahead and try DOL number 2. All right. You want more properties? We love properties. Let's come to what's called a common logarithm. Circle this, these words, common logarithm. And what you need to write is this is a log with base 10. If you have a common logarithm, they will not even write the base down. So let me show it to you this way. Log base 10. Evelyn, what's your favorite number? 3. Will be equal to log of 3. If you just see log of 3 with no base at all, that means the base is 10. That's what we call a common logarithm. And so walking over here, these are the same, I say walking, moving over here, this is the same thing. It's saying the base of 10 raised to the power of 0 equals 1. This is saying 10 to the first power equals 10. That's what this is saying here. This one's saying 10 to the power of x equals 10 to the power of x. And finally, this is saying 10 raised to the power of log x is equal to x. That's what they're all saying. This one, again, is exponential. That is exponential. That is not a logarithm. That's an exponential form. I know it has the log as a power, but that's an exponential. So you would write the word log, and then you would say my base is 10 you would swap these two of x is going to equal to log of x. And that's because this has a hidden base of 10. All right. With that, it says evaluate log of 10,000. So again, I'm going to put equals x. So what's my base this one? 10. You do not have to write a 10 there. I'm just going to go ahead and write this that the base equals 10. So if I solve this, I would say my base to the power of 10, I'm converting it to its inverse, an exponential, equals 10,000. 10,000. Okay, let's use some upside down division, as they call it. 10,000 divided by the base of 10. How many times can 10 go into 10,000? You just cancel a 0 1,000 times. How many times can 10 go into 1,000? Cancel that. And we're down to now 100. How many times can 10 go into 100? 10. How do you know when to stop doing this? When it's all base, the same base all the way across. So this is 10,000 equals 10 to the power of 4. So x equals 4. Log 10,000. Notice every 0 is hitting, it was changing the answer 1 greater each time. All right, part B. What form is this in? Logarithmic or exponential? Very good, because it's a base raised to a power. So if I wanted to solve an exponential, how can you solve an exponential? Yeah, so remember how, and when we do algebra, when we are isolating a variable, how I say we always do the opposite. So if it's like you're trying to solve for x, and you had x minus 7 equals 10, I would say, what's the opposite of 7 or minus 7? You would say plus 7. So if you're trying to solve an exponential, and I say, what's the opposite of an exponential? Your answer should be a logarithm. Yeah, its inverse is a logarithm. All right, so with that, on this one, I'm going to add the word log. What's your base? 10, which you do not have to write. And then you would say that's equal to x, because these two switch places, which equals log of 12. Now, for this to be equal, these bases have to be the same. This doesn't show a base. So what's its hidden base? If it doesn't show a base, what's the base there? 10. Good. So guess what? X equals 12. All right. And one more. Base of 10 to the power of x equals 14. 10 to the power of x equals 14. I do my upside down division. How many times can 10 go into 14? Answer 1.4. And we have a problem. So we got to use the calculator here. And you're going to discover the answer is not as pretty as we'd like it to be. Log of 14. 1 point. All of this. And if you're like, wait, why is that the answer? Why isn't it just 1.4? Well, I don't know the exact answer, but I would tell you, you just keep trying to divide by 10. 10 would not go into 1, but it could go into this one time, or 0.14. And I don't know how. Honestly, I have no idea how to get there. I have no idea. But I trust the calculator. When it tells me the answer is 1.14 as opposed to, yeah, I don't know. I'll just leave it at I don't know. There's your answer. 1, 4. I'll just stop at 6. There you go. I better do a squiggly. Why do I do a squiggly equal sign? That means I rounded. That's exactly right. It's approximate. All right, your turn. I'm sorry. One more time. 10. There's the hidden base 10 to the power of x equals negative 11. Again, upside down division would not work here. We'd say that's negative 1.1. Still wouldn't work. But
It's undefined.
very good. It's undefined. You remembered. Why is this undefined?
Because you can
With logarithms, you remember the domain rules, the third rule that we added? We said logarithms must be positive. No power, nothing raised to a power will be a negative solution. If you remember, we dealt with this earlier. If you have a negative power, that doesn't make your answer negative. It takes the reciprocal. That's all it does, is it takes the reciprocal. So this is undefined. If I type this in the calculator, log negative 11, it's undefined. All right, and now let's let you try your DOL. You can use your calculator to come up with a solution. Now let's talk about natural logarithms. So natural logarithms by symbol do not look like what you would think a natural logarithm will. What it is, a natural logarithm is a log with the base of e. So again, going off of Evelyn's favorite number of 3, a log with a base of e will be equal to, they'll write it as ln of 3. And I think that's because in Latin, the order of the words natural and logarithm were opposite. And I think it was Latin first that they came up with this logarithms, I think. And so there was like logarithma natural or whatever, however they did it. And so it became ln as opposed to nl. But if you see ln like that, that just means it's a log with the base of e. Okay. So over here, this is saying, let me translate these. E to the power of 0 equals 1. This would be e to the power of 1 equals e. This would be saying e to the power of x equals e to the power of x. And finally, again, this is an exponential here. That right there is an exponential form. So if you converted it to a logarithm, we would say log with the base of e. These two, it's the inverse. We need to switch the order. X equals ln x. That's what that one's saying there. All right, so let's get to some math. It says evaluate ln e to the power of 4.6. All right, so if what form is this? It looks like in, like it's inside of something. That's not it, that's an L for natural log. What form is this in? Logarithmic, or is that in exponential form? It's logarithmic. So I want to convert it to exponential. What's my base if it doesn't show one?
Oh, 10.
Nope. That's log. If it doesn't show one, it just says log, it's base 10. But when it says ln, I'm going to make this look like an L more than an I. If it says ln, the hidden base is e. So it's e to the power of x equals e to the 4.6. What's my solution going to be? 4.6. You got it. Try that over here. ln e to the 4.6. Calculator agrees. Second one, evaluate this. Any ideas what the answer is going to be? E to the power of x equals negative 1.2.
Oh, undefined. Undefined.
Why is it going to be undefined?
Negative.
You cannot have the number portion of a logarithm cannot be negative. You can have a negative base, you can have a negative power. You cannot have a negative portion there. Answer is going to be undefined here. I type this in, natural log. Again, you don't have to type in the base. The calculator will know that it's a base of e. All right, and finally this one. What form is this in? Exponential. So if you convert it, you'll write the extra word log. What's my base? Nope. E, that's my base there. These two inverse, they switch, so it's x equals ln of 4. Well, log base e is the same thing as natural log. So my answer here is just 4. E raised to the power of natural log 4 is 4. And finally, here's one just for the calculator. Because E, do you remember what E is as a number? Yeah, if you round it 2.72, we're saying E to the the power of x equals 7. 2.72 going into 7. I had no idea. So let's just type that one in. Natural log of 7. Whoops, not 78. 7 is at 1 point, all this right there. So here the answer would be 1 point. I'm going to write on to the nearest hundredth, 1.95. All right, DOL number 4. All right, we're going to quickly take a look at some of these graphs. So a logarithm is an inverse of what type of function? Exponential. So quick hits over here. On exponential, 3-1, we learned that an exponential, I kind of described it like an airplane taking off. If it's exponential growth, I said it always goes through a certain point. 0, 1. It always went through the point 0, 1. This is an exponential graph, an exponential growth. Let me write that up here. Exponential growth. And I told you it always has an asymptote. It's kind of like a plane. On a plane, you hope never actually runs into the runway. You hope its tires touch the runway, but not the body of the plane. That's kind of the idea, is you have an exponential function that gets really close to something flat like a runway, but it never actually hits it. So that's we had an asymptote, a horizontal asymptote at that. And we said that asymptote is y equals 0. Okay, so what's the math on an inverse? What math occurs for an inverse? You switch x and y. So a logarithm, notice, here's a logarithmic graph. We'll have a, let me put this is a logarithmic graph. I'm just going to write logarithm here. A logarithm will have an asymptote, not at y equals 0, but x equals 0. And that's why the domain is only the positive values. It doesn't actually hit 0, nor does it go negative. But we have an asymptote at x equals 0. It should go through a point. What point should it always go through without a transformation, that is? Not 0, 1. How about 1, 0 this time? Why 1, 0? What math takes place? You switch x and y. So that's how the graphs are related. Does that make sense? So we didn't write it all down. Will the domain be all reals? No. So this domain, will x values greater than 0? Or you could say from 0 with a parenthesis to infinity. What about the range? It'll be all reals. It goes down forever and it goes up forever. So the range will be all real. So YER. So again, these are just switching x and y's from last class. Or you could say from negative infinity to positive infinity. We could do a whole lot of things. I already did the asymptotes, the end behavior. Oh, is this graph increasing or decreasing? It's still increasing. This is increasing. It increases on its domain. If you want to do the end behavior, the two limits for this graph, there are two limits. You would not go left forever. How far left can this graph go? It doesn't go left forever. How far left can it possibly go? To 0. So you would have x approaching 0 for this end behavior. What happens to the y's as you get closer to 0? Negative infinity, you got it. And then this limit over here, you could go right forever. So as we go right forever, what happens to my y values? They get larger, so they go up forever. That's right. All right, so there's your general idea for this. And I'm going to go through the decay a little bit quicker. I don't know if they call it a logarithmic growth. I'll go ahead and do that, though. I'll call this logarithmic growth. I don't know if they actually call it that. So in the next one, we'll put, this is logarithmic decay. And so just some quick hits on this. Does it have an asymptote? Do you see any asymptotes? Does the graph get flat anywhere?
Yes.
Yes. A vertical asymptote. That's not the one I was wanting. Let me try this again. It does have a vertical asymptote. What's the equation of that vertical asymptote? So which one's changing? Or which value is not changing? The x's or y's? If you moved a point up and down this line, the x's never change. The y's change, but the x's don't. That's why they call it x equals 0. If you're wondering, that's how they came up with that, because the y value is always changing on this line. but the x is staying the same. It's constant. Okay, so there's my asymptote, x equals 0. What point should this go through? Nope, not 0, 1, but 1, 0. 1, 0. It goes right 1. Instead of on an exponential, it was the y-intercept at 1. This should be an x-intercept at 1. So 1, 0. That would be decay because it is decreasing. This graph is decreasing. I'm going to skip the rest for the sake of time. You can come back and fill this in if you'd like. Your turn. This is a log with a, by the way, that was because the decay is because the base is less than 1. Growth is because the base is greater than 1. So if the base is greater than 1, it grows. If the base is less than 1, it decays. I'm going to let you come up with what you think the end behavior would be if your base is greater than 1. Ooh, and I need to put the plus on my 0 because we don't actually hit 0. So let me do that on mine. We don't actually get to 0, so I need to put the plus right there. And on this one, I didn't write the limits, but if I did, let me go ahead and write the limits here. As you approach 0, you never actually get there, so it'd be a plus. What happens to my y values? Do they rise, fall, flat, or stop? As you get close to 0 here. Okay, flat, when I say flat, I mean left and right flat. So they rise. And so the answer there would be infinity. And on this one, the limit as we travel off to the right, what happens? Does the graph rise, fall, get flat, or stop? It looks like flat, but it's not actually, I mean, flat would mean like flat. It's still decreasing. So it'd be negative infinity. Okay. No, it decreases, it falls as you go right. All right, with that, now you should be able to come up with your limits. If you don't know, graph the picture, graph it, and then look at it. What should be happening? All right, so now transformations, the inside, remember, is always where the x is. I didn't mean to close that. So this one here, let me actually see if I can add that back. There we go. This one here, question, is that +1 on the inside or the outside? Inside with x or outside of x? Inside. So if it's inside, according to Hyvo, it's horizontal. And now, whoops, started right, Hyvo again. Horizontal. When you add a value, does it stretch, shrink, shift, or reflect? What type of transformation is addition of 1? Stretch, shrink, shift, or reflect? What'd you say? Shift. It's a horizontal shift. Does it lie or tell the truth? Lies. So horizontally, you don't go to positive 1, you go negative 1. Which way is that, Gerardo? Up, down, left, or right? Left. It'd be left 1. So this would be left 1 unit. Okay, next. What's the base if it doesn't show 1? It says the word log. 10. This is the base of 10. Will this be growth or decay? Growth. Thank you, Sydney. It's growth because the base is greater than 1. So it's growth and it's left 1. So notice this graph would have an x value that you could go as far as, but not touching -1. This asymptote would be at x equals -1 because it got shifted left 1. Not only that, this one should go through the origin at 0, 0. Instead of being 1, 0, it's 0, 0 because it went left 1 unit. So there's a transformation there. All right, the next one, I have 2 transformations. Honestly, they should have made this clear and put a parenthesis. I'm going to assume, since they did not put a parenthesis around x minus 2, that the log is only the x. So first question, this negative out in the front, is that inside without x or outside of x?
Outside.
Outside. Does that make it horizontal or vertical? If it's a vertical and a negative, does that stretch, shrink, shift, or reflect? A negative. I hear shift and I hear reflect. A negative does a reflection. This is a vertical reflection. So if it's vertical reflection, it goes across the, remember, reflections are tricky. It'll go across the x-axis. Moving from up to down or down to up, reflected across the x-axis. Now the -2, is that a -2 inside or outside? I'm also going to say that's outside. We'll see if that's how they want theirs. I should look at the picture first. This is a vertical when you subtract 2. Stretch, shrink, shift, or reflect. Shift. A vertical shift.
Okay.
Down because it tells the truth. Down 2. Let's see if their picture agrees. Reflection shifted down 2. So they did. We did do it correctly here. I assumed correctly. It did not shift it up or down, or excuse me, left to right. This is still x equals 0 asymptote. But instead of, and I forgot to tell you, like originally it was growth. This, because the negative becomes decay. This one does not go through the point 1, 0. Instead, it goes through the point 1, -2. This is counting by 2s. That's the point 1, -2. It got shifted down 2. All right, one more. What does a 5 do in front of a log? Vertical or horizontal? Is it inside or out? Outside. It's vertical. When you multiply, does it stretch, shrink, shift, or reflect? It'll either stretch or shrink depending on if it's a truth teller. Is this a truth teller or a liar? So this is a vertical stretch by factor 5. And what about here? The -3. Inside or outside? Inside. So it's horizontal. Subtracting 3. Stretch, shrink, shift, or reflect? Shift. And it's a liar, so right 3. So we should go right 3 and a vertical stretch. So the asymptote is no longer at 0. It went right 3 units. So this should be at x equals 3. My graph is counting by 2s, but that is x equals 3. The point is no longer 1, 0, and it's now 4, 0 because it went right 3. The vertical stretch does not change the x, it changes the y. Multiplying that by 5, 0 times 5 is still 0. So that's why that did not change. There. All right, your turn to determine what the graph would be here. All right, let's now take a look at some real worlds here. It says earthquakes. The Richter scale measures the intensity R of an earthquake. The Richter scale uses this formula shown there, where A is the amplitude in microns of the vertical ground motion, T is the period of the seismic wave in seconds, and B is the factor that accounts for weakening of seismic waves. Describe and analyze the end behavior of the graph of the function R equals all that. So I'm gonna go ahead and type this in. We'll say R. I'm not sure if the R will work, but we're gonna try it out. R equals log A divided by 2.1 plus 5.4, and it does. We have a good little graph here. Let me go ahead and take a picture of it so we can properly analyze this graph. All right, so here's my picture. And specifically, what it wants to know is about the end behavior. Describe and analyze the end behavior. So this graph, if you notice, will not go left of 0, just like the asymptote we've been talking about, x, where it would be x equals 0, but in this particular case, that would be a equals 0 there. That would be the line, because this would be my a-axis, and this would be the r-axis. And so the limit here, the way you would write this, not of f of x, sorry, that would be of r, limit for the r, as your a value approaches 0 from the right side. So as we approach 0, this would go down to -infinity. However, there's one issue, and that is this is real world, and you would not have a negative, and so they would actually stop at 0. We would just cut off this graph. So this part here would no longer be real world. So this is not relevant. This part, not relevant. So I'm going to erase that part out of there. And now, as we go on to the right forever, so the limit of the right the r values as a approaches the right. So as we go right forever, this graph is increasing to infinity. And so that would be my end behavior for that function there. Now on part B, it says now we want to solve the problem. It says find the intensity of the earthquake with an amplitude. That's the A of 250 microns a period That's the t. T is period. And a b of 5.4. So now I'm using this same equation and I'm saying that r will equal the log of my a is 250. My t is 2.1 plus 5.4. Now I'm just going to type this in the calculator and we're going to see what we get. It'll be easier just to copy that and delete that so it doesn't mess up my graph. We said a is 250 and 5.4. The answer would be 7.48 if I round to the nearest hundredth. 7.48 would be my value. And this one we would need to round to. It says, or actually doesn't mention what to round it to. And so the unit, let's see if it says the units here, Richter scale. No, it doesn't say anything. So I'm just going to put that r would equal, or approximately, since I'm rounding, 7.48. That'd be my answer for part B. Part C says, now, same information. It says if the earthquake occurs, and now we've changed the A to 125 microns. T, the period, is changed to 0.33 seconds, and B is now 1.2. What is the intensity of this earthquake? So here we go. Let me just copy this and change our values. So we're now at 125, but they're coming quicker together. So it's not as much movement, but the movement is happening more quickly. That's the period. At and the sizing factor is 1.2. We would get a value of 3.78 when I run this one. So this time, that's all that's changed. That's on my formula. We would have r equals log of 125 over 0.33 plus 1.2, and therefore the r is not equal to, but approximately 3.78. There's my answer to part C. And now finally D. Let's do, this time we're going to search for the amplitude. So now we're saying, what is the amplitude? So that's my unknown. The A is unknown. Whose intensity? That's the R, the intensity. 6.1 with a period. That's the T. And B of 3.7. So this time I'm going to say 6.1 will equal log of the unknown A divided by 3.5 plus 3.7 on the outside. And we would solve this. Now using algebra, you would subtract the 3.7 and we would convert this to exponential, which, and you've seen me do a lot in the calculator. So I'm going to go ahead and just do it this way. When I subtract this, I'm going to get 2.4. 2.4 equals a log of A divided by 3.5. And now from here, what I would do is I would convert this to exponential. My base is 10. So I'm going to say, when I convert this to exponential, 10 to the power of 2.4 will equal A divided by 3.5. And so finally, the last little step here would be to multiply by 3.5. I'll put it in parentheses. So I'd multiply by 3.5. Now, you would need to raise that to the power first, but either way, A will equal, and I'm going to do A equals 3.5 times 10 to the power of 2.4, which is approximately, let's see here, 3.5 times 10 raised to the power of 2.4, 879. This would be the intensity, 879.16, and the unit for amplitude is microns. That would be my answer. Now you could use insolve for this as well. Go to Desmos, click insolve, and you could type in these values here that we knew 6.1 equaled the log of A. I'm going to use an X divided by 3.5 plus 3.7 on the outside here. And I'm going to set Y over here as 6.1 and Y equals the right side of the equation. And the intersection would be your answer, which we know the answer is supposed to be 800. So if I zoom out, I should have a solution right there. 879.16, exactly what we had. So we did do this correctly. With that, You now have a DOL. You can try this problem to stop the video and work it out. All right, let's take a look at an ACP question. This one's really based off of your knowledge of the vocabulary. It says, which graph represents the graph of a natural logarithmic function? If you did not know, you could just type this in the calculator, whoops, as ln of x. Natural logarithm is ln. So you could just say y equals ln of x and look, but hopefully after this lesson, you know which one would be exponential. What's this one right here? Exponential growth. I started to say which is exponential, and I realized that's not the question I'm trying to ask. That's exponential growth. What's this? What's B?
Decay.
Exponential decay. That's not it. Exponential decay. What's the next one? Maybe it. What's D?
That's a log.
Okay, so D is logarithmic, which is the correct answer. This is a square root.
Oh, like where's the rest of the graph?
Yeah, a square root is half a sideways parabola. So that would be a square root there. And a second ACP question. It says the Richter scale is used to calculate the intensity of an earthquake based on the amount of observed motion. An earthquake's Richter scale measurement is calculated using this formula, where A is amplitude observed in micrometers. What is the amplitude A of an earthquake that measures 5.75 on the Richter scale? That 5.75 on this Richter scale, that just goes in for R. So if I did a little algebra, by subtracting 3.75, I would be saying that 2 equals log of A. What's my head and base? 10. So 10 squared would equal A. The answer would be 100.
This is the end of this period.